So everyone gets the reference here? Okay, so you should definitely see Dr. Strangelove or How I Learned to Stop Worrying and Love the Bomb. There's a very, very tenuous link at the best of times. But anyway, I'm here to talk about Rust. This isn't the evangelism talk. This isn't the one where I try and sell you on Rust. I'm assuming you've all sort of heard of it. You understand the basic promise of it, the three virtues, and fearless concurrency, and all these things that we're sold on that are there and they're true. But Rust has famously quite a steep learning curve. I will be giving a little quick recap of Rust, but I'm kind of assuming you've looked at tutorials and got the basics and seen the basic rules of it. But I will take you briefly through them. I'm going to argue for persevering with Rust over this difficult hump that it famously has. I can't cover all of Rust. I can't fix every problem for you. Rust is very much a journey that we're going on. One way of looking at this, the title of this talk, is understanding Rust is the journey that anyone learning Rust takes forever. It's always interesting to see people who are very experienced with Rust on Reddit or the forums or whatever going, oh, I didn't know about that bit, because it's such a rich environment, and there's so many cool things coming out in it, and particularly the async world is changing quite rapidly. And I'll touch on that very briefly at the end. So understanding Rust is the journey, it's the book. How I Learned to Stop Worrying and Love the Borrow Checker is one of the early chapters, maybe chapter 3, where you finally give in and go, okay, I've got to stop fighting this and start working with the language rather than against it. Now, traditionally, you don't. I tell you about myself, and you don't care. But I did work at Atlassian for 16 years. We were fairly early on in the DevOps world. I'm both a sysadmin and a programmer. And I did some fairly early work on continuous deployment of $1 billion order system, as in $1 billion had passed through it by the time we started doing continuous deployment of it. So it's fairly critical. Later on, we started I started talking about Git and explaining Git from the bottom up. That same idea is where this talk came from. The idea of recreate this idea of, okay, you've learned Git, now you've basically tried to rebase and you've broken everything. Okay, here's what you really need to know. Here's how Git actually works. I'm also the author of XCP, which is an experimental clone of the Unix copy command that uses Rust and kernel acceleration and hardware acceleration on modern NVMe drives to create a faster, more interesting copy with pluggable experimental drivers at the back end. But as I say, you don't care about this. You're here to learn about how I learned to stop worrying and love the borrow checker. This is a fundamental driver for this talk. I am using borrow checker in a broad sense. If you're a Rust purist, it covers a lot of things, including some of the type constraints and so on. But people don't talk about fighting the borrow checker. That's what we're talking about. Talking about fighting the compiler and the rules that the compiler puts in place. We're going to go quite advanced here, but I will do a quick recap now, just for everybody. So Rust has, at its basic level, the syntax is very familiar. It's kind of somewhere between C and any number of slightly functional but C-like languages. It does borrow a bit from C++ here in that it uses the ampersand as a reference. In Rust terms, this is called borrowing, and hence the borrow checker. And it has rules. You are not allowed to have multiple mutable references to something. You can have any number of immutable references, and by default, all variables in Rust are immutable, unless you explicitly say otherwise. If they are mutable, a number of rules kick in. You cannot have multiple mutable references. This is because of race conditions. This is because of things like cache coherency. This is just because it's just absolutely insane to have multiple mutable references to something. This is probably the fundamental of Rust. What do you take away? Like many languages, some languages make us better programmers. Haskell's one, Clojure, and Lisp in general. They change the way you think, even if you never use these languages again. Even Java in its day was quite unique in being both garbage collected and statically typed, and created a new way of thinking about APIs. This is what Rust does. It basically, everyone says, oh, I'd never have multiple mutable pointers. But of course, we all do. When you're rushing, you're doing it. And by default, Java has this. In fact, most languages have this idea of basically everything can point to the same piece of data and change it at will. Rust enforces the thing that we say we don't do. And you find out quite rapidly that you do it. And that's where you start fighting the borrow checker. You start going, oh, I should be able to do this. There's another interesting one here, though, is mutability is once you take something as mutable, you cannot have any other reference to it. This is illegal code. Even though rocks, we have a mutable variable, x, we take an immutable reference to it, that's still invalid in the Rust world. Because even if you have one mutable variable and one immutable pointer to both the same thing, you're now dealing with CPU cache coherency issues. There's a reason the C has the volatile keyword, because it's very easy on modern CPUs to have everything looking at the same variable and each one getting a different view of it. So Rust does not allow this by default. Now, all these things can be worked around, and Rust does give you tools for doing it, but by default, it expects you to abide by certain rules. Another interesting one is ownership. Everything has an owner, one. Now, again, there are ways around having that, but by default, Rust only has a single owner, and that ownership is passed around. Here, this code will not compile. This is a compile time. The compiler is doing the work for us here. But because what we do, when we send person to save person is just a struct with a name in it for the purposes of this demonstration. At the end of it, it goes out of scope. And the compiler goes, nope, you handed this over here, you didn't give it back, therefore, this no longer exists, it's gone. Well, one way around this is here, we can return the variable. But obviously, this is clunky as hell, so we can pass ownership back. But no one does this. This is insane. This is just a theoretical way we could think about it. Alternatively, we can use those references we talked about. This is why it's called borrowing. When you pass it in with the ampersand, that says I'm taking a reference to this. It's a temporary reference, and once the function returns, it will revert back to where it was called from. This is a quick recap of the rules of Rust. So now I'm going to take a bit of a left turn and talk about garbage collection. We talk about borrow checkers, and this is how you're introduced to it, all these mutability rules, ownership, and so on. But there's another way of looking at Rust, which is the compiler is your garbage collector. See, all languages are garbage collected, even the ones you don't really think of as being garbage collected, like C. Even the ones you don't think of as being garbage collected like Rust. Rust is famous for having its garbage collector torn out of it early on in its development, along with a lot of other runtime type things like green threads, and becoming a pure compiled language with no runtime by default. But even C is garbage collected, except that you do it manually. You do a malloc, and you do free. Anything that's on the stack is automatically reclaimed. Anything that's malloc goes on the heap, and then you have to manually free it. And as you may notice, the second pointer is not freed. Therefore, it goes on existing for the life of the program. If you do that enough, eventually your program will be garbage collected by the kernel, which will shut you down for this. And if the kernel doesn't do that, eventually the operator will have to hit the big red button because the whole machine falls down. We've all done it. We've all done the fork bomb at university or our first job. And it happens. So one way of looking at the borrow checker is to think of it as garbage collection. So when we moved that object from my function to save person, what we did was we passed the ownership on. When it got to the end of that, the compiler said, well, you haven't handed this back, therefore it's gone out of scope. It no longer exists. What the compiler does, for all intents and purposes, is inject the free operation for you. When the object goes out of scope, when it's no longer visible by anything, then the compiler GCs it. Now, this is slightly different to the JVM, for instance, where the JVM can, when nothing is pointing at something, it can reclaim the object, but maybe it won't. Maybe it'll keep it in the old generation. And it could live on for the life of the program because the compiler thinks you might want to use it again at some point in the future. Rust is a bit different here. It actually definitely deterministically calls the free at the point where it goes out of scope, at a known point, if you're looking at the program correctly. So it also allows you to hook in. There are a couple of places. The compiler is fairly agnostic about the code, but there are a couple of magic places in the compiler where you can hook into it. And this is the trait drop. Now, traits are kind of like interfaces in Java for the sake of this. They're a lot more complicated. They're basically Turing complete. But at the simplest level, they are like a Java interface. It says, if you implement this and you implement drop, then this will be called. So basically, it's a magic hook-in point to the compiler that says that we are going to, when I'm about to shut this object down, I will call drop for you, which allows some interesting side effects. As well as garbage collection, we can garbage collect on pretty much any resource that we want to be cleaned up at the end of the program or the end of its scope. And we know exactly when that will be if we design our programs correctly. So in this particular case, let's imagine theoretically how you would implement a wrapper around the Unix file operator. So Unix returns on libc open, it returns an int, which would be a U64 on modern operating systems. So we create a structure that wraps a U64, an unsigned 64, I should say, and then we create an implementation of this. So it's kind of like the body, the methods attached in a class. We do open, and it takes a path. We calls libc open and stores and returns the wrapper around it of the open file. Now, so far so good, but we don't have a close on this. We don't have a bunch of other operations, but there are a whole other bunch of traits that you can implement, like write and read and so on, that you would do as part of producing a fully fledged file wrapper. But you also implement drop. Rather than close, you just implement drop, and that calls libc close. So that means that if we have this program, some file, that opens a file, reads and sums up the values in it, and returns the sum. Rust does not require you to say return. If you have an unterminated, the last operation, the last expression, if it's unterminated, is returned as the return type, a U64 in this, an unsigned 64 in this case. So what's going on here is that Rust will inject close at that point. We no longer need to have close because the compiler says to you, when this thing goes out of scope, I will close it for you. You don't need to do that anymore. This leads to some interesting Rust idioms. So for instance, this is a common thing you'll see. You just create a temporary syntactic block, and that block says this is how long this file should be open for. When you get to those closing braces, inject the file close, please. This makes sure that your file is written in a timely manner and isn't held open if something else needs to read it. To close the drop could potentially even call flush and make sure it goes out onto the physical hardware. Sorry. Another way of looking at this is one of the things that people spend the longest time trying to understand about Rust, and it's one I still struggle with occasionally, is this. This could be expressed as a lifetime. This is the lifetime of the file object, the beginning and its end. That tick there, the file, is the tick is the syntax for a lifetime. Now, Rust injects these itself 99% of the time. It knows what the lifetime of everything is. That's how it manages to know that things need to be dropped at certain times. But it's helpful in Rust to think in terms of scopes of lifetimes. How long will something live? And then when it stops living, it will be shut down in a coherent way. It also allows some other interesting idioms, which is everything in Rust is an expression or close to. That means everything can potentially return data. So in this particular case, we can read the file and then return the data from that block and then assign that to a data structure, and the file is closed down for us. This is, again, idiomatic Rust. There's another way of calling drop, incidentally. I'm only mentioning it here because I will use it later for clarity, and you will see it in the standard library some places. You can explicitly drop something. Most of the time it's clear, it's more idiomatic Rust to use braces and sort of implied lifetimes. I think it's clearer. The braces, I think, give a very visual clue to what you're doing there. But you can call drop directly, and that will make the object disappear. You'll notice that the drop does not have an ampersand inside the brackets. So the ownership has been passed to the drop operation. We're saying this is now the end of this object. Therefore, this object is now dead. No one owns it anymore. It will be shut down. So now we're going to go a little bit lower. We're going to go into the stack and the heap. This is some basic computer science stuff. I think everybody's familiar with this to some degree. The stack is assigned to the function at hand. It's largely created at the start of the program and reused across all invocations of various functions, and data builds up. So this is in a C-like program. By this point at the end of the program, you would have an array, an integer, and two pointers to point to data that's on the heap. The heap is long-lived. It's allocated on as needed by the kernel in blocks as you request them, and then you hand it back a pointer that you're expected to clear up unless you want the program to live forever. When you get to the end of the program, most of this will be cleared up, including pointer 2 will disappear, but the data it's pointing to will not, because nobody ever bothered to call free. You can allocate on the heap in Rust. It is a slightly different way of doing things. There's something called box. Box is basically malloc. Worst name ever for what it is. I don't know why. I think it might be a passing reference to boxed variables in Java before box became the normal thing. There used to be like boxed and unboxed variables in Java. I think it technically still does, but they're effectively interchangeable now. Anyway, so we create a fixed size array on the stack. That's the interesting thing about the difference between a heap and a stack. The compiler needs to know at compile time stuff that's going to be allocated on the stack. It needs to know the size of it. So anything that's variable size needs to go onto the heap. So any variable size vectors, strings, things like that all end up on the heap sooner or later. And then when we call box, what happens is that array is moved into the heap, and we are handed a box reference back. And interestingly here, once that box goes out of scope, the end of the lifetime of the box, drop is called. And drop will clean up the heap. So you don't have that dangling pointer. It is very, very hard to create a dangling pointer in Rust. There are ways of doing these things. Rust famously has unsafe code. You can call safe Rust and unsafe Rust. Unsafe Rust, you can do pretty much whatever you want. It's not discouraged. Everyone will use unsafe at some point, but less is definitely more in the case of unsafe. And certainly when it comes to memory, you better be sure you know what you're doing. So this is what box looks like. This is actually, it's quite simple in some ways. I'm going to poke down into the standard library in a few places here and just show you kind of under the hood. I hope it clarifies a few things. This is I told you there's a few hooks into the compiler. This is the other end of the hook into the compiler, the opposite of drop. Box is magic. If you look at box new, you'll notice that box new calls box new. That's infinite recursion. That will blow up in microseconds normally, except that just above it is Rust CBox. And sorry, the font on that the color is not great. Rust CBox is a magic instruction that appears twice in the entire standard library. The other one is in the vector allocation, I presume for performance reasons. And it says, in compiler, inject magic here. But the rest of the time, you pretty much can do pretty much anything a standard library does. In fact, if you try and use Rust CBox with anything except box new, it will blow up and say, nope, you can't do that. That's impossible. This is one of the few places of deep magic that's in the standard library. The rest of the time, you actually have you could rewrite your own standard library, and people have. Obviously, there is a drop for box, and that just does a deallocate. That's pretty much it. Rust's got its own allocator, but it's mostly a wrapper around malloc or some kernel calls. So as you can see here, we do a box new. we get the, at the end of the lifetime of that box, it gets deallocated. So you can never have a dangling box, at least not without going through some serious hoops. Box is used extensively through the standard library. It is the main way that you create heap. In fact, anything that is variable length, as I say, will be box. It's also used in a couple of other places that help you get around some of the weird issues of Rust. In particular, it's a sense of cleaning up after itself. So I want to talk a bit about that in the concept of sharing. Sometimes you want something to be referenced from multiple places. Things like graphs, if you're building a tree pointing to data, maybe you've got a large piece of data sitting in memory and you don't want to copy it around. You would like to have multiple places where it's referenced. There's a number of ways of doing this in Rust. This is the idiomatic way. This is the lifetime-based way of doing things. In this scenario, we have an image. The image we're going to assume is quite large. We want to share it between a couple of different structures used to process the image. So this is the lifetime of the image. It's never explicitly stated. It's implicit. It's defined largely by the brackets that surround the objects or the whole function. And we want to create a reference and place it in multiple places. Now, as I've said, we're allowed to have multiple immutable references to data. So we just hand it into the structures. However, because Rust can infer a lot of lifetimes, it can't infer all of them. Sometimes you need to make a promise to the Rust compiler. And that's what that tick A is. That says, I promise whatever reference goes in here will live longer than this structure. The structure's lifetime is A. That must be shorter than the thing that is being pointed at. So in this scenario, we have the image lifetime is larger than effectively the same size, ends at the same time as the thing is pointed at. The structures point at something which outlives them or lives as long as them. So this is fine. I realize this is probably unhelpful. Everybody comes across this in Rust, and everybody struggles with it. I still do. But most of the time, you hear about lifetimes in Rust, and they can get quite complicated when you get down into the standard library and some very esoteric ways of programming in Rust. But 9 times out of 10, this is all you need, the only time you need to interact with lifetimes explicitly, except in one other case, which we are going to cover in a bit. But what if you don't want to do it that way? What if you want, for instance, to have circular references? Now, they are possible in Rust, but you can't do it with lifetimes but if something is a circular reference, by definition, it must outlive itself to a degree. So there's another structure called RC, reference counter. This puts data onto the heap, but also allocates a heap or shared counter as well. This means that we can do something interesting. We can do a clone. Now, clone is not kind of like copying, but not. Clone is something that you explicitly implement for a type in Rust, and what it does is largely up to the type in question. So whenever you see clone on an object, you need to go and read the documentation for it, because it can mean different things in different places. With a string, it means just a bitwise copy. Just take a whole copy of this, memcopy the whole thing. In the case here, it means something different. It means that I want to share the references. So if we go back, we can actually see when we create this, that's backwards, sorry. When we create the RC, we move it onto the heap, and we create a counter within the count of 1. That's the number of references. When we clone it, we increment the counter. The clone operation increments the counter and returns a reference to the shared counter and shared data. When the first reference goes out of scope, in this case we're just calling drop for clarity, the counter is decremented to 1, and when the last reference to it and the counter goes to 0, it's reclaimed. Drop will literally go, if count 0, then right, we're reclaiming this. This is interesting because it allows us to do certain things that are simplify the whole lifetime issue. So this is something I don't recommend directly, but you probably will need to use at some point. We basically load the image here, and rather than taking references, we can use RC instead, because we can take multiple copies of RC and they will all point to the same data, but they will be cleaned up when they go out of scope. So when all of them go out of scope, when the last RC is cleaned up, the counter will return to 0, and you will get a cleaned up environment. So far so good, but so far everything we've been talking about has been implicitly single-threaded. Threads change things quite a lot, and this is kind of, I think, one of the takeaways from the talk. Hopefully we'll introduce some ideas to you that you'll find useful. Let's imagine a simple threaded program. It's going to use threads. We've got a configuration that includes a pointer to a large image, so we want to share it rather than copying it around. Sometimes copying is fine if you just got a few small objects. In some cases, Rust will just automatically copy things like ints around for you if they're not mutable, because it's literally faster than creating a pointer to it. So we're going to say we're going to have a little program. The program loads the config, takes a reference to the object because we want to share it between the threads, and we know that it's immutable and we can share things, right? So that's fine. And we're going to do a thread join at the end. So basically, we spin off. We imagine there's some work happening in the front end as well, and then we spin off a thread for the back end to do independent work, probably on a different core on your computer. And at the end, we will join. So we know, for instance, that the lifetime should work, but it doesn't. That should be the other way around. So the binding, this should theoretically work. The life of config lives longer than that thread, right? So what happened? Why did the compiler should presumably know join means end of the thread, therefore we can basically reclaim it at the end. Unfortunately, we can't, because threading is inherently non-deterministic. And this is basically a fundamental of computer science, that you cannot guarantee when any given program will finish. It's called the halting problem. The lifetime of a thread is unknown and unknowable. Even if this worked, even if the compiler could learn about joins, there's nothing to say that the thread doesn't create more threads. It can't even fork something off. It could send the object around somewhere else. You don't actually know what the lifetime actually is anymore. So we need to think at a slightly higher level. Hence, things like RC, possibly. As I mentioned, RC allows you to create multiple pointers to something on the heap, and each one of them is owned. So while you're sharing the data, each one is a true object in and of itself, and we could just send that in. By the way, I should have said this earlier, for confusion, the double lines there is the shorthand for closures in Rust. Basically, it's just an anonymous function that captures this environment. The move there says this object now belongs to you, Fred. It's not being borrowed, it's being moved. The difference between the borrowing and the move again. It's just a way of saying this now belongs to the Fred. So theoretically, this should work, right? Because we're now pointing to things on the heap. We have a blessed method of having shared owned variables. It should work, right? No. It fails, but it fails for different reasons. And this is an interesting bit of Rust you have to learn if you're going to do threading, but also if you're going to do any async. What's happening here is this: send. It does not conform to a rule that the standard library has set, which goes, anything that goes between threads must be send. Now, what does send even mean? Well, we'll come back to that in a minute. We're going to briefly revisit traits. Traits can also be markers. There can be certain magic traits that do nothing but say, you must conform to the rules that I've imposed around this trait, or this will not compile. In this particular case, this is the signature for spawn, the thread spawn. FN once incidentally, is the formal type signature of the closures. Those two bars resolve to an FN once. You can just implement FN once and create a closure by hand if you want, longhand. In this case, we're saying that anything that is passed into the closure must be send and static. So it must conform to two rules, that it is send and it is static. And anything it returns must be send and static. And we'll talk about static in a second, because it doesn't mean exactly what you may think it means. It certainly confused the hell out of me for a long time until I found out. So there's two special traits inside Rust that are, again, slightly magical, but not that magical, that have nothing in them, and they exist purely to be a marker, to set certain rules. Data can be sent if it can be sent between threads safely. This means no unsafe mutable data, no dangling references, that sort of thing. It must be something that can be transported through memory. It can be in a safe way. Subtly different is sync. Sync says not only can it be sent, but it can be shared. You can have multiple references to it between different threads. It can be manipulated in a safe manner. Generally speaking, in practice, this means mutexes and atomics, and those are generally either at least operating system supported, and very often CPU level support, like physical hardware in the CPU. Things like semaphores and so on that you're probably familiar with. This is why the traits are marked as unsafe. Anything that wants to conform to this explicitly will end up being unsafe. It will always be talking to the operating system, to the hardware, to something very low level. And Rust allows this and explicitly states we are a systems operating language. Sooner or later, you are going to end up getting down in dirty with the kernel, at least. But also, it has another interesting, and again, this is an interesting aspect to it. And again, this is the only place it's used in the whole standard library that I can see. Auto. It's one of the few places that has magic automatic inheritance. If you create a struct where everything in the struct is send and or sync, you will automatically be promoted to send and sync. So you never actually need to explicitly say, I am send and sync. It will happen automatically. Generally, it'll be because you're using things that are safe, that are designed for this. Now, before we jump on, I will address the other issue, which is static. If you've used Rust at all, you've probably come across static in the first context here, the left-hand context. Static strings. Static here means something very similar to Java, C++, where it means this is created at compile time and is baked into the text area of the ELF executable that you are about to run. But there is another usage for this static, and I think I prefer that they actually created a marker trait that said static, capital letter. That would be simpler, clearer. But a static structure or any kind of object is static when it contains no external references. It is entirely self-contained. This is what allows something to be sendable as well. It has no hanging references, and particularly it has no references to outside lifetimes. So this is not very well documented in Rust, and I thought it's important. There is a difference between static in different contexts. And in particular, in the case of async and threading, it means objects must be self-contained. So to go back to our original issue with RC, we can see that we tried to send an RC, a reference counted heap allocated object, through to a backend thread. But that won't work because RC is explicitly not send. That is what the bang at the front of those send and sync means. It explicitly says, even if compiler accidentally thinks that I am sync and send, do not assign me this, because I am not. The reason being is that shared counter. That's a race condition. That is an unprotected object that is going to be incremented and decremented, mutated from multiple places, multiple threads potentially, and that is not allowed. Incidentally, if you just for clarity, the question mark sized means everything in Rust automatically has a size associated to it, unless YOW explicitly doesn't. However, there's a question mark size, which means I don't care if it's sized or not, I'll take anything. It's weird, it's interesting, and I only mention it because it's literally the only place that syntax is used. The question mark also is kind of famous in Rust for its elegant error handling system, which I'm not going to evangelize today. But here it means something different, and it means it's an optional size type, and this is the only place that's actually used inside the standard library. Here's another piece of compiler magic. So what can we do instead? RC does not work. It is not, and it is definitely not send. Well, there is an alternative to RC called ARC, atomic reference count. This will work because under the hood, it uses atomics. It uses a hardware-accelerated, shareable, cache-coherent YOW sizes. YOW size is just the unsigned size. Basically, there's equivalent of the C version of it. It's basically whatever the maximum size objects can be in Rust, which is pretty much unsigned 64 on modern 64-bit CPUs. ARC itself explicitly is send and sync, and if you dig around inside the standard library, you will find that there's a lot of atomics, mutexes, and so on in use under the hoods to make sure it's safe. It explicitly implements it, but it doesn't. But it has a cost associated with it. But you will see ARC a lot in any threaded code, and you will see tons of it in async code. Talking of async, this is kind of the elephant in the room situation. Async is the hot thing in Rust right now, but I'm not going to cover it here. Now, everything I've just talked about is necessary to start doing async. It's necessary to start doing async as it stands right now. The interesting thing about Rust is, Rust async, is that its main implementation is threaded. And async itself, the async Rust implementation, is not compatible with basic Rust. There is not a clear boundary between the two. A function must be async or not, and it's very hard to call between the two. So when I discuss this with people and say, should I be using async right now? The answer is, I think no. Because right now, async is going through a little bit of a change. Or at least it's being discussed. There's a fascinating article. I recommend, if you're even remotely interested in this stuff, reading it by Evan Schwartz, that puts forward the idea that other people have had, but really sums up this idea. Currently, the Rust async implementation of choice is called Tokyo. It's a work stealing implementation. It runs multiple threads, a big pool of threads, and those threads have queues attached to them. And if one thread is really busy, other threads can pull data off other threads' queues. And it basically load balances at the runtime level. This means that everything must be send and sync and static, because it's definitely going to be moved, or possibly going to be moved between threads. But if you have a implementation of async that's a little bit more like what other languages like, say, Node use, then you don't need that, because if it's a single threaded async runtime, then you don't need to send things between threads. So you don't need any of this stuff. Or you could do something else, which is called a thread per core, or fixed workload is another way of thinking of it, where you create a certain number of threads, but when you assign the object onto a thread, it stays with that thread forever. Now, this is not always optimal, but it's often it's a better way of doing things because it makes programming much simpler. You can get thread starvation. But the reality is you are probably not going to come across that. Unless you are Fastly or AWS or Cloudflare and operating at the edges of the internet at massive scale with unknown number of clients and so on, you're probably not going to need work stealing. In fact, you're probably not going to need async at all. The primary use case for async is massive, massive scalability. And the reality is, if you don't know you need that, then you probably don't. So I'm probably going to get flamed to a crisp on the internet if this part of the talk ever gets out. But I would say async is not quite ready yet. There is many research work and so on, many projects out there trying to clean up async, to make it compatible with normal Rust, to remove some of this send and sync and static requirements, to basically make it a little bit more ergonomic. So I would recommend following it now because it's a really exciting time. This article and the Reddit and forum threads that span off from it were really fascinating. So I recommend keeping an eye on things there. So that's it. Hopefully this has been helpful if you are using Rust. Hopefully it's been a very, very steep learning curve if you haven't. Sorry about that. In terms of reading lists, I would recommend the Rustlang. That's traditionally been sort of seen as kind of like an under the hood, very deep dive, but in fact it's actually very readable a lot of the time and explains a lot of things that aren't really covered by the standard tutorials. There's an emerging book called Rust Design Patterns. Generally speaking, any normal design patterns, especially object-oriented ones, don't apply to Rust. Rust is too different in that sense, so you need new types of patterns. You need things to explain stuff like this, like, okay, when do you need to use send and sync, and how can you work around it, and what are your other options? And again, I cannot recommend this Evan Swartz article enough. It's beautiful to see something where it's just, it explains things so well, and the person is so excited to share these insights with you. So that's basically the talk. I hope it was of some use to you. Like and subscribe, as the kids say. This is the GOTO app. They would like everybody to give some feedback. I'd certainly love to. I did actually rewrite a chunk of this talk this morning based on feedback from the last one. So if there's anything I could have included or been clearer about, please let me know. But other than that, that is hopefully a rather rushed introduction to the mid-level of Rust and why the borrow checker is your friend at the end of the day. Thank you.
Thanks, Tim.